Here we're going to talk about graphing motion in physics, position time graphs, velocity time graphs, and acceleration time graphs. We'll start with the basics, position time graphs. So here's a position time graph, and we'll have a look at what this means, what this tells us. First of all, we know that this is a straight line graph, which tells us that the object is undergoing uniform motion, so that means it has constant velocity. And we can find the velocity of the object by calculating the slope. So if I take a couple of points here, say right here, points on the line, we want to take points that are far away from each other, one near the start and one near the end. And you would use a ruler for this, so these would be straight lines. So here we have the rise of the graph, and here we have the run of the graph. And to find the slope, I'm sure you recall this from previous courses, slope is equal to the rise over the run. And so we'll work that out. Here we've got 45 minus 5, which will give us the rise, and we've got 4.5 minus 0.5, and that will give us the run. So there's our rise and our run. And when we work that out, we get 10 meters per second. So that gives us the velocity of this object, indicated from this graph, and it's positive. You know, the slope is positive, the positions are all positive, and we may have been given a direction. We weren't given direction here. If the direction, if we were told that the positive direction was north, then we would say that here the velocity of the object is 10 meters per second north. Now in this case it's very simple motion, uniform motion, because the velocity is constant, and we can tell that because the slope is constant for this graph. That won't always be the case. We could see a situation in which the slope is not constant, and we'll look at that next. So here, what we've really calculated is the average velocity by finding the slope, but the average velocity is the same as the instantaneous velocity at any time, because in this example, the velocity never changes. Let's see what happens when the velocity does change. A curved position time graph shows us non-uniform motion, which means that the object's velocity is not constant. A smooth curve indicates uniform or constant acceleration for the object. If we find the slope of a line segment joining 2 points on the curve, if I choose these 2 points and draw the line segment, and find the slope of that line segment, then that slope gives us the average velocity for that time interval. The slope of a tangent, which I'll do in red here, gives us the instantaneous velocity at that time. The tangent touches the curve at only 1 point. So this tangent touches the curve at about 3 seconds. So if we find the slope of that tangent, like so, with our rise and our run, then the rise and the run are position 2 minus position 1, over time 2 minus time 1, which is another way of saying rise over run. And so, reading from the graph, interpolating, we've got 41 meters or so minus 0.5, or rather 5 meters. And then for the corresponding times, we've got 5 seconds minus 2 seconds. Put our units in there. And so when we work that out, we get an instantaneous velocity of 12 meters per second. And that's in the positive direction. So if we assume that positive is north, then that means the direction of our instantaneous velocity is north, because the slope we got was positive. Now the principles we just saw apply to velocity time graphs as well, but there's more useful information we can get from a velocity time graph. If we find the slope of a velocity time graph, that gives us the acceleration of the object. If we have a straight line velocity time graph, that tells us that the acceleration is constant. So this graph shows us several straight line segments, which means we have several different accelerations, but during each of those time intervals the acceleration is constant because we have straight line sections of the graph. Just as we saw that the slope of the line segment joining 2 points of the graph equals the average velocity on a position time graph, the slope of a line segment joining 2 points on a velocity time graph gives us the average acceleration for the object. And if we had a curve on this graph, we could find the slope of the tangent to find the instantaneous acceleration for the object. Now let's find the displacement for this object in the first 10 seconds. So the displacement equals the area, and again we'll assume positive is north. So our displacement is, the first shape we see is a triangle, and notice that it's negative. We have to be careful about that because that tells us direction. So the area for that triangle is 1/2 times the base times the height, and then we're going to add the area of the two really small triangles. And then the large rectangle that's positive, so length times width. So I've colored in the areas that we're going to find, the large triangle that's negative, and then 2 small triangles on either side of the rectangle. So this is one small triangle over here, this is another small triangle over here, and then we're finally finding the area of this large rectangle in here. So that's where those values come from that I've substituted in here. And so for the displacement, we've got -6 meters plus 1 meter plus 1/2 a meter plus 10 meters. So we get +5.5, or 5.5 meters per second. And because our positive meant north and we got a positive result here, that means that the displacement is north. Going one more step, this is an acceleration time graph. Again, the math is similar. So this is an acceleration time graph, and if you find the area for this graph, it will give you the change in the object's velocity, and the slope of the graph gives us the rate of change of acceleration, also called jerk. So you could find average jerk, you could find instantaneous jerk, and those are just different kinds of rates of change of acceleration. So if we find the area of this graph from 0 to 6 seconds, we've got a positive area, which I've colored in blue on the left, and a negative area that I've colored in blue on the right. Each of those is the same size, or same magnitude. So we've got 2 times 2 length times width for the first area, plus 2 times negative 2 to give us the second area. So when we add those together, we get a total of 0. So the change in velocity over that interval for this object is 0. If we want to find the slope of this graph, well, you can see that each of the lines is horizontal, which means that the slope of each line segment is 0. So slope is 0. No calculations necessary for that one, and that's for the entire interval. So that tells us that the rate of change of the acceleration is 0, or the jerk, the average jerk for the entire interval is 0. But you'll notice that there are vertical lines that are dashed lines, and that's because when the acceleration does change, we can't have more than one acceleration for any given instant in time. So at 2 seconds, if you look at that instant, at 2 seconds right here, we have a dashed line because we can't have a value of positive 2 meters per second squared for the acceleration and a value of 0 for the acceleration at the same instant in time. That's physically impossible. So the dashed line shows us that there is some very short time interval during which the acceleration changes from 2 to 0 in that case. And so, but because it's such a very, very short time interval, we show a dashed vertical line. So that's what those lines mean. And that's an overview of graphing motion.